Okay, so our next speaker will be Professor Dehan. He's a colleague of BA from University of Toronto in the Department of Statistical Sciences. So today he'll be talking about, I think, fighting noise with noise, causal inference with many candidate instruments. So Dehan, take it over.
Okay, so yeah, I would first like to thank Limbo's introduction and also thank the organizing committee for organizing this fantastic conference. And today I'm going to talk about fighting noise with noise, causal inference with many candidate instruments. So this is a joint work with my PhD student Cindy Zhang and also my colleague Limbo here and Stanislav Workshop. Around like 40% of people in the world are overweight. And in this talk, we are interested in whether the overweight can affect the quality of life. The data we use comes from the Wisconsin longitudinal study. And so to measure whether a person is overweight, we use the BMI value. So when the BMI value is greater than 25, a person is overweight. While the BMI value is less than 18.5, then the person is underweight. When it's between 18.5 and 25, the person is normal. And to quantify the quality of life, we use this HUI3 index. And the higher the index is, the better the quality of life is. And here we show a scatter plot. And from this scatter plot, one can see that when the BMI value is greater than 25, there is a negative association, while the BMI value is less than 25, there is a positive association. Of course, we know that the association may not be causal. So the PPT is very small. So can you see my full screen or just?
Yeah, I can see the full screen.
Okay, yeah, no problem. Okay, so we know that like in this observational study, the association does not imply a correlation. For example, one may have some confounders. For example, some lifestyle. For example, if a person say likes eating junk food, this habit may increase his or her BMI value. And meanwhile, when a person is eating this junk food, he or she may feel happier, which improves this quality of life. And of course, in this observational study, we are unable to observe such as a confounder, so we cannot directly adjust them to make the causal inference. To overcome this problem, there's another chat. Let me see. Okay. Okay, so to overcome this problem, and one popular approach is called the Mendelian randomization. So the Mendelian randomization is actually an instrumental variable approach. And in this approach, one uses genotypes as those instrumental variables. So these genotypes are actually randomly assigned when passed from their parents to the offspring during the meiotic process. So they are very unlikely to be affected by those confounders. So in particular, you can regard these genotypes as like a random dice, and we can roll it again, which mimics a randomized chart. So for those of you who do not know about the instrumental variable, here I will give a very brief introduction. So here we are interested in estimating the causal effect of X on Y. And an instrumental variable Z is defined as a variable which satisfies these following three properties. First, this Z should have an effect on X. So this effect is non-zero. Second, Z cannot directly affect Y. And finally, this Z cannot have a correlation with this confounded U. And the second and third assumption, we can summarize it as the Z can only affect Y through this X. And under these three assumptions, this Z is called an instrumental variable. And one can write z to x to y, this effect equals z to y times x to y, where this x to y is a causal effect of interest. And by moving this z to x to the left-hand side, we can see this x to y equals z to x to y over z to x. And this is called the Watt's ratio. And if we have a finite sample, the corresponding estimate is called the two-stage least squares. However, these, like those natural experiments, are imperfect. So we can have a lot of genetic variants. However, most of them are irrelevant. So in the past, when people are performing Mendelian randomization, one often rely on those expert knowledge, basically find some important biomarkers. And the modern approach is to apply some, let's say, the GWAS study. So suppose we have, say, P candidate genetic variants, where this P can be millions. And one can just run a screening procedure with, say, basically run X on Z1 to ZP and find those important Cs. Of course, then in this way, we can find some relevant genetic variants. However, this also has another problem. So for those SNPs that pass the GWAS test, they may still be invalid due to pleiotropy. So this pleiotropy is actually an interesting phenomenon in genetics where one genetic variant can affect multiple traits simultaneously. So for example, here, if we have a Z1, which is a genetic variant, it can affect multiple traits, including this risk factor X. If it happens that there is another trait which is on this arrow between this Z1 and Y, then Z1 can affect Y not only through X, but through other traits. So in this case, this Z1 is called invalid. And if we recall that, or if in the instrumental variable approach, we can use the Watt ratio to obtain the causal effect. And in this case, if we treat this invalid Z1 as a valid instrument and use the ratio, Watt ratio to obtain the causal effect, this causal effect will be biased. So therefore, we need to remove these invalid ones. So there are some existing solutions to solve this problem. So here I summarize these references. Their ideas are actually quite similar. So for those valid instruments, we know that their ratio will be around the true causal effect. And but for those invalid ones, they may be biased. And but these bias can be very different depending on how strong one violates these IV assumption. Therefore, they assume a plurality rule assumption, basically. And in this case, they assume that these valid ones, they have a plurality, satisfy plurality rule. And then one can basically use a mode finding algorithm to identify these valid IVs. So here's a summary of the existing solution. So the first step is to perform some GWAS based on the strength of the links between Z, J, and X and find those relevant instruments. And then one can apply a mode finding algorithm to identify those valid ones. And finally, one will do a refit and to estimate the causal effect based on two-stage least squares. So now we will perform a toy simulation to repeat this procedure. So in this simulation, we consider 50,000 candidate IVs. So in this case, Z1 and Z2, they are invalid ones. And Z3 to Z7, they are valid ones. And for the remaining, they have no relationship with this risk factor X. We consider sample size equals 500. And for the unmeasured confounder U, we just generated from standard normal. So for all these arrows here, so we generate this relationship using linear regression models. And the true causal effect is set X to Y is set as 2. So for this GWAS procedure, we will just use a procedure in GWAS et al. 2018 JSB paper. And so this GWAS procedure contains 2 steps. The first step is a marginal screening, so which is like the showing independent screening proposed by Jianqing Fan. And so we just select the top 500 candidate CRs based on the absolute value of the marginal correlation. So we just rank these absolute value of marginal correlations and obtain the 500 largest ones. And then we will fit a debiased lasso model, basically do a refined estimation on X on these selected variables. And then we will obtain those coefficients. Then we'll threshold those small coefficients to 0. And for those non-zero coefficients, they are the IV selected after this GWAS procedure. We repeat this step for 1,000 Monte Carlo round, and on average, there will be around 21 candidate IVs left. The good news is that among these 1,000 Monte Carlo rounds, we always include those 7 relevant IVs. So everything looks okay now. And then we apply the second step. So we use those 230 squares and obtain the causal estimates corresponding to the selected variables. And then we apply a mode finding algorithm to identify those valid IVs. And the final step is to do a 2-stage least square refit. However, it turns out that the causal effect estimates are biased. Here, the average bias among 1,000 Monte Carlo studies is negative 0.22, while the standard error is only 0.02. And we also apply the constructing confidence interval based on the original procedure, and the coverage probability is only 0.07 when the nominal level is 0.95. So something went wrong here. So you may wonder, well, what went wrong? So recall in step 1, on average, we select 21 candidate IVs, and these candidate IVs always include 5 valid ones and 2 invalid ones. It also includes 14 irrelevant ones, but these 14 irrelevant ones are not randomly selected from the close to, say, 50,000 irrelevant variables, but they are those variables with spurious correlation. Spurious correlation means that they have no population. So the population correlation between this variable and the X is 0. However, their corresponding sample correlation is actually large because we have a selection procedure here. So these irrelevant variables, they actually have a large sample correlation with the treatment X. And to see this phenomenon clearly, we will just combine all those estimates from all 1,000 Monte Carlo round. So we will have approximately 21,000 estimates here. Here we just plot the histogram. And we color these estimates using different colors. And for these orange ones, they're corresponding to the estimates of irrelevant variables. And the blue ones are those valid variables, and the green ones are invalid IVs. So from this histogram, it's clear that the mode are actually corresponding to those irrelevant ones. So this illustrates the reason why we actually, when we apply mode finding algorithm, there's something wrong. So now I would like to answer why these irrelevant instruments are also alike. So to answer this question, we consider the simplest case where we have an extreme confounding. So now, suppose we have a single unmeasured confounder U, and X is only determined by U. So you can interpret it as X equals U. And if there is a spurious instrument, so this spurious instrument Z has no population correlation with X, but it has a large sample correlation with this X. And since this X is completely determined by this U, this Z can be interpreted has a large sample correlation with this U. So we use this dashed line to denote this large sample correlation. And then now if we treat this Z as a valid instrument, and we use a ratio to obtain the causal effect, one can see X to Y equals Z to X to Y over Z to X, which is covariance between Z, Y, and over covariance ZX. And in this case, the covariance ZY actually equals this. So there are two passes from Z to Y. One is Z to U to X to Y, and another is Z to U to Y. And for covariance between Z and X, this is Z to U to X. So if we take a ratio, one can see this ratio has two terms. The first term is x to y, and the second term is u to y over u to x. And one can see this, the first term is a true causal effect, and the second term is a bias. And this bias does not depend on how strong this C to U is. As long as it's non-zero, the bias is always there, they are the same. So this explains the reason why the bias is the same for all errant instruments. And interestingly, this bias is also the same as the bias from the OLS estimate by ignoring this confounder. So basically, if we regress y on x and use this to estimate the causal effect, the bias is also this. So here, I just give you a message that adjusting for the spurious instrument is similar as just run an OLS without adjusting for those unobserved confounders. So now this explains the reason why these errant instruments are alike. So now what we know so far are all valid instruments are alike and all errant instruments are alike. And for those invalid instruments, they are different from each other, so they can be everywhere. As we know that for those errant instruments, if we use a ratio to obtain a causal effect, they will be biased. So what we need to do is to remove them. So we need to distinguish those valid instruments from those errant ones. To solve this problem, the key idea is to generate some pseudo variables. So in particular, suppose we have a sample size n and we have p dimensional of genetic variance, then we have a design matrix C, which is n by p. What we do is to randomly permutate the row of z and get a new z star, which is also n by p. And then we will just stack z and z star together as an n times 2p design matrix. Then we will apply our GWAS procedure of x on z star. And after the GWAS procedure, there will actually be 4 groups of variables left. The first 3 groups are those valid instruments in the original z, invalid instruments in original z, and irrelevant instruments in original z. For the fourth group, we notice that this z star, we already randomly permuted the rows. So we actually destroy the relationship between this z star and the risk factor x. So in other words, for all those variables in this z star, they are errant variables. And if those variables in this z star still pass a GWAS procedure, they must still be errant variables. And we also know that these group 3 and group 4, they are alike. Basically, their corresponding causal effect estimates are similar. And moreover, we know that for these group 4 variables, they are generated by ourselves. So we know what these variables are. And if they pass the joint thresholding, we can still track them. So the idea is that we will use the behavior of the variables in group 4 to infer the behavior of group 3. So one can see from this histogram here. Now, this is all those estimates corresponding to those variables past the GWAS procedure, but now we use x on, we regress on x, z, and z star. So this gray color are actually corresponding to those group 4 variables, so errant variables in z star. And these orange ones are those errant variables in z, and the blue one and those green one corresponding to valid and invalid instruments in z. So now we can see these gray variables and the orange variables that corresponding estimates are similar. So in particular, in order to remove these errant variables, what we do is that we will remove those causal effects within the range of those pseudo effect estimates. So you can see after we remove these pseudo estimates, we will have a scatter plot like this. Then we will apply a mode finding algorithm to identify those valid IVs. And the final step is to do a two-stage square refit, but you use these valid IVs. So this is our procedure. So we have some theoretical guarantees, but as a time constraints, I won't talk about the detail here. So briefly speaking, we have 2 theorems. So the first theorem shows that for those spurious IV, their corresponding causal effect estimates are concentrated within a region, where this region, beta star plus C star here, you can just regard it as those OLS estimates. And basically the expectation of OLS estimate. And these minus D and plus D, this D actually depending on those parameter values. Of course, here the theory relies on the linearity assumption of all those models. And the second theorem says that for those valid IVs on some regularity condition, these causal estimates are concentrated around the true causal effect beta star. So under the assumption, if this D is less than the absolute of this C star, then one can separate those spurious IVs and valid IVs. And then we are able to identify those valid IVs. Finally, I will talk about our real data application. So we use data from Wisconsin longitudinal study. So participants were graduates from Wisconsin High School in 1957 and their siblings. And the exposure of interest is the BMI value. And here we only use BMI value greater or equal to 25 because they're corresponding to the overweight group. And we have 3,023 unrelated individuals. And the outcome of interest is the HUI3 index. And we first perform a crude analysis. So what we do is just adjusting for those observed cohorts. We have those age, gender, and education. And then we regress this HUI3 on this BMI by adjusting for the baseline cohorts. Then we find that the corresponding causal effect is negative 0.011. So this indicates 1 unit BMI increase associated with 0.011 unit decrease in HUI3. Then we will apply the Mendelian randomization procedure. So after pre-processing, we have around 3.7 million SNPs. And for the baseline cohorts, in addition to age, gender, and education, we also consider the population stratification, where we use the top 6 principal components of this whole genome sequencing data. And to apply our procedure, we will generate the same number of pseudo SNPs by permutating the row of the Z matrix. So here Z is like the 3,000 times around like 3.7 million. Then we have Z and Z star. Then we apply the GWAS on the Z and Z star. And finally, we have 44 SNPs correspond to the Z left and 42 SNPs corresponding to those pseudo variables. So now we plot those estimates corresponding to these variables past the GWAS study. So this red dashed line actually separates these true and pseudo variables. So the left are those estimates corresponding to the true variables, and the right are estimates corresponding to the pseudo variables. Then we will apply our second step. So what second step says that we will calculate the range of those estimates corresponding to the pseudo variables, so which are those black dashed lines. Then we will remove all those estimates within this range. So we'll remove all these points, and there will be 4 points left, the 3 here and 1 here. And the step 3 is to apply mode finding algorithm, and we find the mode here. So these 3 variables are identified as valid instruments, while this variable is identified as invalid. And the final step is to do a refit. And it turns out the causal effect in this case is negative 0.039. So to compare, we will apply the mode finding algorithm, basically the 2-stage hard thresholding with voting in GWAS et al. 2008 JSB paper. So we first apply their procedure on the true SNPs only, so apply to the Z only. And these estimates are corresponding to variables past the GWAS procedure, and the mode finding algorithm will identify these blue square points as valid IVs. And after refit, it turns out the causal effect estimate is negative 0.008. And in order to validate our method to support our finding, we apply the GWAS et al. Procedure on the same data set. But in this case, we not only apply it to Z, but we apply it to Z and Z star together. So this yellow dashed line still separates these two variables and pseudo variables. And if we apply the mode finding algorithm on those variables that pass the GWAS study, then we can see that all these blue square points, they are identified as valid ones. However, in this case, we know that this their method is very likely to be wrong because on this right-hand side, there are those pseudo variables, so they must be irrelevant. However, for those mode finding algorithm, they actually identify as valid. Therefore, their corresponding causal effect estimate, which is negative 0.011, is also likely to be wrong. So now we summarize a comparison of all those results here. So for our proposed method, one standard deviation increase in BMI will lead to roughly one standard deviation decrease in the HUI3 index. And for Guo et al.'s method, the mode finding algorithm, if we ignore the spurious instruments and apply to the true Z only, the causal effect is 0.2 SD. And if we apply it to the true plus pseudo variables, the causal effect is still 0.2 SD. And if we apply the crude analysis without adjusting for those unmeasured confounder, the causal effect is also 0.2 SD. For this third method, basically it's this method, we know that it is very likely to be wrong because it identifies those irrelevant variables as valid ones. Therefore, for this causal effect estimate, it is also likely to be wrong. And so for this, the second and the fourth one, they are also likely to be wrong. And also this this result also validates our previous argument. If we ignore the spurious instruments, it has a similar role as basically ignoring those unmeasured confounders. So you can see the second method and fourth method, their corresponding causal effect estimate are similar. Finally, I will give a summary. So in this talk, we consider the Mendelian randomization, which is a powerful tool for causal effect estimation. However, there are some challenges for Mendelian randomization studies if we consider a whole genome sequencing data with millions of SNPs. So to overcome this challenge, the first step is to find those relevant IV. One can use a GWAS procedure to fulfill this goal. And the second step is the second challenge is the pleiotropy, and one can find the mode of those effect estimates to remove those invalid IVs. But what we find is that if we combine these two steps together, there will be a bias due to the spurious variables in the GWAS. And the spurious IV bias is potentially a serious problem because ignoring those spurious IV bias has a similar effect as ignoring those unmeasured confounding bias. Therefore, we propose a fighting noise with noise procedure, and we use those pseudo variables to correct for spurious IV bias. So that's all for my talk, and here are some references. Thank you very much.
Okay, thank you, Dehan, for the very nice talk. Maybe we have time for one question. I see there's a hand up from Thomas.
Yes, could you just say a little bit about to what extent this method relies on no interaction assumptions or even in no correlated interactions? Yeah,
Okay, so I think our method, I think we rely on the linear mode assumption with only the main effect. Yeah. So if there are some like interaction effect between these, say for example SNPs, those IVs, and at least it's unclear to me. That our method can still apply to those cases.
Thank you.
Yeah, just a quick comment, Thomas. I think this method is orthogonal to the no relation assumption. So I think what you're doing is using linear models, but if you have other methods that take into account of the interaction term, then I mean, you can apply the same technique. I think this development is orthogonal to your model for IV estimation. Okay.